You're here because you want to master chemical equilibria with a University of Cambridge graduate. Let's begin. I find that chemical equilibria is a very application-heavy concept, very similar to reaction kinetics, where mostly the questions test about your understanding of concepts and various applications of the different concepts itself, whether it be through open-ended questions or calculation questions. So to start things off, chemical equilibria is denoted by this reversible sign over here, which shows that a reaction can proceed from either direction, whether it's a forward reaction or a backward reaction. When you see this reversible arrow sign, be sure to take note that this is definitely a chemical equilibria question. Next, at any time, you must know that both reactions are always occurring. It is not that one reaction is always going and the other one stops. That is not really the case. It is just that the rate of one reaction could be faster than the rate of the other reaction. Another thing to note is delta H that you see for a reaction that is reversible indicates the enthalpy change of the forward reaction. And you just need to know that the backward reaction has the same magnitude of enthalpy change, but it has the opposite sign. So if the forward reaction is positive, then the backward reaction has a negative enthalpy change. Moving on to dynamic equilibriums. When a reaction has reached dynamic equilibrium, this means that the rate of backward reaction is equal to the rate of the forward reaction. And this also means that there is no net change in concentration of reactants and products. And again, do take note that both the forward and backward reaction are still taking place. If you look at the graphs, you can see that the concentration of A and B start to decrease at the start, and then the concentrations of C and D start to increase at the start. However, the rates of the reactions start to decrease as we go along, specifically the rate of the forward reaction. And that's because the concentrations of your A and B start to decrease and the concentrations of your C and D start to increase. This means that the system is reaching the dynamic equilibrium. And if you look at the rate of reaction graph against time, you can see that the rate of forward reaction is much higher than the rate of the backward reaction, and therefore the reaction is proceeding forward. But over time, the rates of the forward reaction will decrease and the rate of the backward reaction will increase until the point that they are both equal and the system has reached dynamic equilibrium. Now if you look at the equilibrium constant, here we have a typical reaction where A plus B gives C and D, and the molar ratios are as such with A, B, C, and D. When you look at this, the equilibrium constant is equal to your products concentration over the reactants concentration. And the powers are to the power of the molar ratio. And for your units, whenever you have to determine the units of your equilibrium constant, just take each square bracket for a Kc equation. Each square bracket is a mole per dm cubed. So when you cancel all the square brackets out using a little bit of math, your final units is dependent on the amount of square brackets either at the numerator or the denominator. So for example, if my final is 1 over a square bracket to the power of 1, that means my units are mole to the power of minus 1 and dm cubed. Do take note that Kc is constant at the same temperature, and it does not change when you change concentrations. I'm going to be emphasizing this a lot throughout this lecture, so please just take note of this, because this is a very typical trap that examiners can give for chemical equilibria. Next, we learn about homogeneous versus heterogeneous equilibriums. So homogeneous equilibriums are when substances are in the same phase, whereas heterogeneous equilibriums are the opposite. The substances are not in the same phase. So when we look at homogeneous equilibriums, we must take note that there are several pointers. For example, H2O liquid is often emitted from the Kc expression. And this is mainly because H2O acts as the solvent of the entire medium. And because of that, your concentration of H2O remains relatively constant because it's in so much excess. Imagine being embodied in water. The amount of water molecules are just infinitely greater, I would say. And therefore, a change in H2O is very insignificant. And because of that, the concentration of H2O is relatively constant. And we incorporate this concentration of H2O into the Kc itself because it is a constant as well. So we often would not put concentration of H2O inside the Kc expression. And another point is that solids are also often omitted from the Kc expression because solids have constant concentrations, and therefore it follows the same principle. They are often incorporated into the Kc. Now let me introduce to you a very key answering technique for chemical equilibria, the ICE table. So whenever we encounter a calculation question for chemical equilibria, you must know to use the ICE table, because the ICE table accurately would tell you how to calculate your Kc itself. Or if you're given a Kc, it will help to tell you the initial concentrations of any reactant or the initial concentration of a product, so on and so forth, as long as we have the necessary information. So we want to put our equation at the top, and for ICE, I stands for initial concentration, the change in concentration, and the equilibrium concentration. And then you just fill it up accordingly, according to the context of the question. How you use the ICE table is with the equilibrium concentrations of the whole reaction. You can use these equilibrium concentrations to find your Kc, or vice versa. With the Kc, you can find equilibrium concentrations of your reactants or your products. So just take note that the concentrations in your Kc equation only represent the equilibrium concentrations. Anything else that is not at equilibrium should not be put into the Kc expression. Now we move on to the equilibrium constant for Kp, or for gaseous state. And it follows pretty much the exact same principles, except instead of concentrations, we're going to use partial pressures instead. So this again would be products over reactants, and the powers are all to the power of their molar ratios within the equation itself. Again, the units are found when you cancel out all the partial pressures, and each partial pressure that you see is a Pascal or ATM or a bar, depending on what unit the question gives you. Kp is also a constant unless temperature changes, and it does not change when partial pressure of gases change. Again, another key pointer to take note. Also, solids and liquids inside an equation for a Kp expression are not included because they relatively do not exert any pressure on the system itself. Now on to some insights from your equilibrium constants. Sorry, there's a typo. So the value of your equilibrium constant shows the position of equilibrium. For example, since these equilibrium constants are your products concentration over reactants, if your Kc or Kp is greater than 1, this means that the concentration of products are relatively higher than the concentration of your reactants. And because of that, this usually means that your forward reaction is favored. However, if it's the opposite, where your Kc or Kp is lesser than 1, this usually means that the reactants concentration are higher than the product's concentration, and this generally means that the backward reaction is favored. And because of that, you can roughly tell the position of equilibrium. So this one, it shifts to right, or lies mainly on the right, and this one lies on the left. And equilibrium constants do not give any information about your rates of your forward and backward reaction. And naturally, since it doesn't give info about your rates, it doesn't give info on the time taken to reach equilibrium. So just take note of this. Now, how does delta G have any relation to chemical equilibria? Well, delta G, as pointed out by delta H as well, if you see a delta G for a chemical reaction in equilibrium, this usually shows the forward reaction. And delta G less than 0 means the forward reaction is spontaneous, but then the backward reaction will not be spontaneous. Again, for the backward reaction, it always has the same magnitude as the forward reaction for delta G, but the sign is the opposite. Now, if delta G equals 0, that means the reaction is at dynamic equilibrium. And for delta G greater than 0, that means the backward reaction is spontaneous and the forward reaction is not spontaneous itself. Lastly, there's an equation over here that you should memorize because you can be told to apply this at any given point. Delta G equals to negative RT ln K. R is the gaseous or the ideal gas constant. So this is 8.314. And temperature is in Kelvin. So just take note. And ln K, where K is the equilibrium constant. Going on to some factors that affect chemical equilibria. So we have this principle called the Le Chatelet's principle. And what Le Chatelet has said is that if a system is in equilibrium and is subjected to any change to disrupt this equilibrium, the system will respond in such a way to counteract the effect of the change imposed in order to re-establish this equilibrium. So you can think of a chemical equilibrium as a naughty and stubborn boy. If you try to put a change on this boy, or you try to give it any instruction itself, this boy is going to do the exact opposite and counteract the change itself. Now, here are some examples of the factors that affect your chemical equilibrium. One such one is the effect of concentration or partial pressure. When that happens, the system naturally would respond in such a way to remove the concentration itself. And because of that, you will favor the reaction that will remove this extra concentration. So in a case where A becomes B, and you increase the concentration or partial pressure of A, the system will respond to decrease the concentration or partial pressure of A. Therefore, it will favor the forward reaction, and because of that, your position of equilibrium will shift to the right. Now take note again that changing concentration or partial pressure does not affect the Kc or Kp, and it is only temperature that will affect it. Now moving on to effect of pressure and volume. So this one is a bit tricky. Do take note that this only affects systems with gases naturally. Now if the total pressure of gaseous mixture increases, whether you increase the pressure or decrease the volume, the system will respond to reduce the pressure by reducing the number of gaseous molecules. So you want to favor the reaction that has a side that has a lesser gaseous molecules. And because of that, your position of equilibrium will shift again according to which reaction you favor. Now there is a very special case where an inert gas is added. And this one is a bit confusing. So if I add an inert gas at constant pressure, this means that the total volume would decrease. And because of that, the partial pressure of each gas decreases. And reactions that gives more gaseous molecules is favored. And the position of equilibrium will shift accordingly. However, if I add my inert gas at constant volume, the total pressure would increase. This is because if you imagine a system, a closed system with gaseous molecules inside, and I add an inert gas, there's naturally going to be increase in pressure within the system. But because the pressure increases, but the number of moles of my original gases do not increase, the molar fraction may increase, or should I say, the molar fraction decreases for the original gases, but my total pressure increases. And it will be in such a way that because molar fraction times the total pressure gives the partial pressure of the gas, this means that the partial pressure of the original gases remains the same, and therefore the position of equilibrium will not change. Now how about temperature changes? According to Le Chatelet's principle, if the temperature increases, for example, the system responds to favor the endothermic reaction to decrease the temperature. You can see that when temperature increases, the endothermic reaction is favored, and then when temperature decreases, the exothermic reaction is favored. And do take note that temperature does affect Kc and Kp. And this is because it influences the equilibrium levels of reactants and products according to the which reactions are favored, whether it's the exothermic or endothermic reaction. So if the forward reaction is favored because of temperature changes, the Kc and Kp or Kp will increase because more products are formed. Because remember, your Kc and Kp is defined as concentration or partial pressures of products over reactants. And it'll be the exact opposite if my backward reaction is favored. The Kc or Kp will decrease. So here's a summary of the answering technique whenever you have to answer a chemical equilibria question with regards to Le Chatelet's principle. Number one, you want to state the change in the equilibrium system. And then number two, you want to state how the system will respond to the change, which is the counteracting of the change itself. And then number three, you want to state where the equilibrium position shifts, whether it's to the left or to the right. And number four, if it is required, you have to state the effect on Kc or Kp and the composition of the new mixture. Now we move to the effect of addition of a catalyst. So catalysts actually increase the rate of reactions, but it increases the rate of the forward and the backward reaction to the same extent, because it lowers the activation energy of the forward and backward reaction to the same extent. If I draw my energy profile diagram, you can see that for a reaction with a catalyst here, with a lower activation energy, let's say this is EA2, and this is EA1, we can see that EA2 is lower than EA1 for both the forward and backward reaction. And it decreases both to the same extent. And therefore, because of that, the catalyst increases the rate of the forward and backward reaction to the same extent. And therefore, it actually does not have any effect on equilibrium positions. But because it increases the rates of both your forward and backward reaction, the system will reach equilibrium faster. So here's an example that you need to know for chemical equilibriums. One of them that is widely tested and widely referenced to is the Haber process. So do remember this equation where N2 gas plus 3H2 gas gives ammonia gas itself. And do note of these molar ratios. You just need to be able to derive these molar ratios by balancing the equation. The delta H is also exothermic. You don't need to remember the number, but I just put it there just for your FYI. And then the usual temperature is 450 degrees Celsius. The pressure is 250 atm. And the catalyst is finely divided iron. Now for this tree, it's better if you just memorize these three conditions itself. It doesn't take a lot of effort. Now, you have to understand the principles behind choosing the temperature, the pressure, and the catalyst. So for the temperature, normally one would decrease the temperature because the forward reaction you want it to be favored because it is exothermic. And therefore, if you lower the temperature, the position of equilibrium will shift to the right and the yield of my products will increase. But you must know that for industrial purposes, or like the industrial reason itself, why I cannot lower my temperature that much is because if I lower it too much, the rate of reaction, more specifically the rate of my forward reaction, would be hindered. And because of that, if you cannot have a high enough rate, it will influence the yield of my product as well. So we use a compromise temperature that is not too low and not too high to obtain reasonably high yield. And the compromise is 450 degrees Celsius. Next up is pressure. So for pressure, normally one would increase the pressure as well. Because if you look at this equation, the side with lower gaseous molecules is the right side. So why would I want to increase pressure? Increasing pressure would favor my forward reaction because it is the side with the lesser gaseous molecules, and my position of equilibrium will shift to the right. And therefore my yield of my products will increase. But for the industrial reason, again, increasing the pressure too much leads to very high capital costs. The building of the metals and pipes and the various machines that you require to increase a pressure is just way too high of a cost. And therefore, you will use a compromise pressure. So 250 atm is used. Next, the point of the catalyst is just to ensure the equilibrium is reached faster. Again, speed is king. We need high speed for industrial purposes. But the catalyst again has no effect on the equilibrium position and the yield. But how is the yield of NH3 or ammonia improved further in the industrial process? Well, when you establish equilibrium, the gases are actually cooled while maintaining pressure. And when you cool the gases, you condense ammonia and you collect it as a liquid. Because of that, when you constantly collect ammonia from the system, the concentration of your product is always going to be lower. It's going to be low and close to zero, and therefore your equilibrium position is constantly shifting to the right. You're always favoring the forward reaction in order to produce more product according to my Le Chatelet's principle. So that's it for chemical equilibria. Again, I must emphasize that this topic is very application heavy, and I would advise that instead of just memorizing this topic, you should be spending some time outside of lessons to do more practice in order to get used to the typical chemical equilibria questions. So if you like this content, be sure to hit the subscribe button so that you can get more frequent updates. If you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past test papers and go through any doubts or clarifications you require and show you how my online class is the best course for you. I'll see you in the next video.